Okay, you may proceed. So let me give you the intro. So welcome to the revision session for the stats 2. Here we have Ankit, who is the TA and the mentor for the last two terms uh, for this degree, and today he will be doing some important concepts of the quiz one. Whatever the concept that are important. So and this is not only one session. We have a session for maths 2 also tomorrow on 3 to 5. So do join that session also. We'll circulate the mails. So yeah,
Any Python session?
no, for Python we don't have. No, for Python. No.
Okay.
Ankit, I have made you the co-host. Maybe you can proceed from here.
Okay, thanks Abhishek. Hello everyone, welcome to the session. In this session, we will be covering all of the concepts that come in quiz 1, that is starting from week 0 up to week 4. And before getting any further, let me clarify the format of the session. So this session is not going to be very problems oriented. I'm not going to solve a lot of problems, just like what happens in a solve with us or a PYQ session. But what I'm going to do is have a little bit of balance between the concepts and the problems. So more of this, you can consider this session more of concept oriented, and we will be focusing a little bit less on the problems. Okay, so this will ensure that any of the doubts that you will be having in any of the concepts, because understanding the concepts, having the fundamentals cleared is very, very important. Only then you will be able to approach any problem. And okay, yeah, I will discuss problems also, but not that much intensively. That's what I meant. Okay, so yeah, that's a little bit about the format of the session. So let's start. I hope my screen is visible, right?
Yeah. So, Ankit, are you give us important topic to coming in Q1?
Quiz one. Okay. What I will do is, as I go along the concepts, I will point out which concepts are important. Okay. But I will cover almost all of the concepts. But I will just point out which are most important from the perspective of the exam. Okay. Yeah. So let's start. So in week 0, so let's start from week 0. So in week 0, what we had was what we already knew, but it was just like a refresher of the basic concepts of probability. Okay? And little bit, you can consider it like it was a revision of statistics 1, and a little bit going into the direction of statistics 2, what you need to study, right? So we will start from week 0, and the very first topic that was there in week 0 was basics of statistics and probability, that you may be very, very comfortable with by now. Okay, these are very basic things. I don't think I need to explain it in any detail. All of you are very comfortable with it, but nevertheless I am just going to talk about it a little bit so that it's refreshed in our discussion, and we are into the context of what we are going to discuss. So we started looking at things, some things which are deterministic and some things which are not deterministic. For example, you may have learning about the motion equations and many scientific equations. Those are very, those follow very exact rules. Okay, you can exactly predict at what point some particle will be, but some things are not predictable exactly. Like you can't predict that when you toss a coin, it will land heads, or it will land tail. You cannot tell that thing with certainty, right? And for these things we need probability and statistics. Okay, so there are a lot of examples of such type where you don't have you don't have the confidence that you can predict the outcome. Okay, so yeah, that's where we that's why we study statistics, and these are just some basic things. The starting thing about when we start learning about statistics, the thing we start with is we have an experiment. Whenever we are doing some kind of thing where we need to know something, we call it an experiment. And whatever is the outcome, that we call outcome. Whatever is the result that we are trying to predict, that we call outcome. So for example, if we take the example of a coin toss, we say that we are tossing the coin, that's an experiment, and outcomes can be either heads or tails. Okay, so these things are you are very comfortable with. Then we have concepts like sample space and events. These things just map to whatever we studied about set theory in maths, and we just apply the set theory to the concepts of probability and statistics. Okay, so studied there into this situation, and we get sample space and events. So what are all the outcomes from an experiment that we determine with a set that is called a sample space? And what is an event? Event is just a subset of the sample space. Okay, so these things you have been studying all along, so I don't need to spend much time on this. You have already seen that you can do operations on events like union, intersection, complement. Once you define an event, then you have a clear idea of what you are trying to predict. Then when we delve into a little bit more about probability, we have some probability theory. We are basically trying to formally study probability. Okay, we so in our daily life we usually say that uh, suppose we have two things. Okay, two possibilities of something happening. We say that this is going to be this is more likely to happen than the other thing. Okay, so for example, suppose two teams are playing cricket match, and you say that this team is likely to win, is more likely to win the match than the other team. But in probability, what we are trying to do, we are trying to quantify every likelihood, every possibility. Okay, so and to follow that we need some kind of a theory, so we call that probability theory. And these are some other things that you will look at. Then the basic properties of probability, you have these things that we already discussed that you can define events in terms of sets. So whenever you have an event which does not have any element, its probability is 0. Okay, so for example, take the example of a coin toss. What's the probability that it will take, suppose example, 0 for tails, 1 for heads? What's the probability that it will take value 2? It's 0, right? It will not take any value in the sample space. So these things apply. Just you have to map all the things about set theory here. Nothing new. Then these are all distributions and conditional probability. Yeah, so there are two kinds of distributions. The one is discrete distributions and another is continuous distributions, right? So sometimes we have outcomes which are countable, finite, and those can be fit into a finite set. In that case, we call them discrete distributions. And in other cases where you cannot fit them into a finite set, in those cases we call them a continuous distribution. And we have a lot of examples. Then we will look at this concept of conditional probability and these things. I have just put it here, okay, just for your reference. But we will discuss about them more, and I hope that you all know, so I don't need to discuss about it in any more detail. Yeah, so now we are moving into a direction in which we will study more and more of this formally. So then we study about random variables and events. Okay, so earlier we were just talking about sample space and events in terms of sets, and after we and now what we are trying to do, we have defined some random variables. What is a random variable? Random variable is basically a function with domain as the sample space of an experiment and range as the real numbers. So for describing the probability, we already defined some sets called sample spaces and events. Now we are defining another function on top of the sample space, okay, which is called a random variable. And what it does is it puts some kind of a numerical value to the events. Okay, so that is a random variable, the concept of a random variable. And the range, you already know, the range is all the values that it can take. Then the most important part of week 0, in my opinion, was this last section that was about probability mass functions and important distributions. Okay, all of the previous things that I discussed till now, you already know, and you have been studying till from the high school level, but these things are a little bit new and have been presented in a slightly new way. So that's why these are important. So what is a PMF? Okay, meanwhile, I see that several hands were raised. So, okay, if any one of you have any doubts, you can raise your hand. I will ask one by one. And yes, PDF will be provided for this. Don't worry. Okay. So PMF, what is a PMF? You have already seen this in statistics 1, but nevertheless, I will discuss. So we see that we have a random variable. So we saw that whenever you are doing some experiment, there are some outcomes. We put all of the outcomes in a set and we call that a sample space. When you take some subsets of that sample space, we call them events. Right. Now, there comes a new concept of random variables. Now, random variables are just mapping the values of sample space to some other numbers. Okay, uh, so a random variable will represent any of such numbers. For example, we have the example of a coin toss. It can take values heads or tails. So heads and tails forms our sample space. Now we define a random variable called x, which will take values 0 or 1. So we have mapped heads to 1 and tails to 0. So that's the purpose of a random variable. It gives a numerical value to it, and it's just a function. Okay, now those random variables can take some values, okay, and they can have some associated probabilities with them. So if we have a fair coin, then x can take two values 1 and 0. X will be taken with probability half, and 1 will be taken with probability half, and 0 will also be taken with probability half, right? So then we have some properties of PMF. As you know, whenever you have a sample space and you add the probabilities of all of the elements of a sample space, it will always be equal to 1. And all of the, and because of this, because all of them have to be equal to 1, all of the probabilities related to each of the elements in the sample space, or probability of the random variable taking some value, has to be between 0 and 1. Right. Then we have some examples of random variables. So we saw the example of a coin toss. In case of a fair coin, it is a uniform random variable. Why? Because all of the values taken have equal probability. In a similar way, we have several different kinds of distributions, and different based on the distribution, we call the random variable differently. So we have a Bernoulli random variable, then we have a binomial random variable. So these are very basic things that you may be familiar with. So finally, in week 0, we studied about different kinds of distributions. So these are very foundational and basic thing that will be useful in all of the courses, all of the weeks that are going to follow, and also in future. So here we have a few. So these are not just these are not this is not a complete list of distributions that are possible, but these are just very representative, and these are very common, that are very frequently encountered in our real life. So let's look at so first of all, let's look at what are the distributions. So first one is the Poisson distribution. Then we have a geometric distribution, hypergeometric distribution, then negative binomial random variable. So distributions, so whatever the random variable takes some distribution, then we call that random variable with that distribution's name. So for example, if you take the example of a Poisson random variable, this is generally associated with the numbers when we are taking some value between a time interval. So suppose there is a shop and you count the number of customers coming at the shop in some time interval. So you set the time interval as, for example, 20 minutes, and you count the number of people uh, coming in the 20 minutes interval, then it will follow a Poisson distribution. So these kind of things follow Poisson distributions. Poisson distributions. Then geometric random variable. These all have some real life, uses, and these are very common. That's why we have listed it here. That's why, yeah. So this was all about week zero. Actually, there is a lot of content, but I have tried to condense all of this in these 6 to 7 slides. Now here we have a question related to this. All of the questions that I am going to solve in this session are going to be from a previous terms quiz 1. Okay, so these are all taken from some previous terms questions. So here we have a question. An analyst is responsible for conducting emissions inspections on bikes. During the inspections, the analyst found that 10% of the bikes failed the inspection. Okay, let X be a geometric random variable which denotes the number of bikes the analyst inspects until a bike fails an inspection. Assume that the results of each inspection are independent. Okay, based on the above data, we have to answer a few questions. So what is the range of X? So what is the range of a geometric random variable? Okay. This all information you will be given, right? So the information on this slide, whatever I have presented here, this will be available in your exam. So whatever all the important distributions are there, along with their PMF and PDFs will be given. So in case of a geometric random variable, we know that the range of values that it can take are 1, 2, 3, and so on. Okay. And so here it says that X be a geometric random variable which denotes the number of bikes the analyst inspects until a bike fails an inspection. So there are a lot of bikes and the analyst is inspecting one by one, and it's given that 10% of the bikes fail the inspection, and X is the random variable which denotes the number of bikes analysts inspect until a bike fails an inspection. So in these kind of situations, you generally understand that the random variable is geometric. So you all must have played Ludo. So when we play Ludo, what happens is we just roll the die multiple times, and a person is allowed to start playing only if he or she gets a 6 first. Okay, so the number of times a person will have to throw the die to get a 6, that follows a geometric distribution. So this kind of in these kind of situations we get a geometric distribution. So here also it's clearly written that is geometric. So clearly the range of X will be, either it can happen that when analyst is inspecting, in the very first inspection, the very first bike that is inspected turns out to be defective or just fails. It can be 2 also. It can be in the third also. So the range of X is going to be from 1 to infinity. Okay, this is very basic. Now it is based on the same question. Now it's asking what is the probability that the first failed inspections occurs on the analyst's 5th inspection. So in this case, we have to calculate some probability of a random variable which is following some geometric distribution, taking some value. So we have to find the probability that X takes value 5. So here we are given that this analyst found that 10% of the bikes failed the inspection. It means if we consider all of the bikes during a general inspection, the probability of getting a failed bike is 0.1, okay, or 10%. That's why the value of p is 0.1. You can get this from this line. Now you all know the probability, how to calculate the probability of a geometric random variable taking some value. Okay, so we have to calculate the probability that x will take value 5. So it means that the if the analyst finds the bike fail on the fifth inspection, it means that all of the four times the all of the four bikes that came before the fifth bike were okay, or they were functioning correctly. Okay, so those are not failing. So the probability will be 0.9 raised to the 4 times 0.1. So this is just basic uses of calculating the probability. But I am just explaining because this is related to very basics. Okay, so this was all about week 0. Uh, if any one of you have any doubts in the concept we discussed, you can ask. No one? Okay, we will then move ahead now. So let's come to week 1. Let's come to week 1. So in week 1, we we studied about two main topics. Okay, it was just the starting week, so there was not a lot of content, and we studied about basically joint marginal and conditional PMF of two random variables and the joint marginal conditional PMF of more than two random variables. Right. So before this, even in a statistics 1, you may have studied the how do you calculate the probability of a single random variable, how do you deal with the PMF, those things. Just before, we solved one question related to a single random variable. There we did not have multiple random variables, right? Just x we had, which was following a geometric distribution. But in this week, we will be dealing with two or more than two random variables. But first of all, we discuss two random variables. How do you calculate the joint, marginal, and conditional PMF? So the first topic is joint PMF for two random variables. Okay. So first of all, you already know what is a probability mass function. Probability mass function is basically what are the values that x can take and what are the associated probabilities. This information is called the probability mass function. Okay. Now, what is the joint PMF of two random variables? It means what is the probability that the two random variables will take some value together. So in this case, we don't have just one random variable, but two random variables. So what is the probability that the value will be taken together? So x takes value t1, y takes value some particular value t2. Okay. So this is called the joint PMF. So here we have an example, tossing a fair coin twice. So we can denote x as the outcome of the first toss and y as the outcome of the second toss. Okay, and we can uh, calculate multiple probabilities related to this example. So in this case, a simple example has been calculated, and this is always going to be same in this case, right? So all of the joint PMFs are going to be same, and here is a tabular representation of this example, calculating the joint PMF. Then we had the marginal PMF. What is marginal PMF? So in case of a jointly distributed random variables, we have two random variables. Okay, so we are generally interested in finding the probability that both of these will take some value together. But in case of the marginal distribution, we are interested in finding the probability that a single random variable will take some value. Okay, so but you know that whenever you are throwing the coin two times, it's not that just one coin is being tossed. You are tossing both the coins, so something is coming on both the coin, but you have to consider, but you are interested just about a single uh, coin. Okay, so you say that I will just consider the probability that the first coin will take some value t1, but it will correspond to, or but for calculating this, what you have to do, you will have to add over all the probability, all the possibilities for the other coin. So for example, let's take the coin toss example. So both the coins can take 0 or 1 value. So what are all the combinations? 0 0, 0 1, 1 0, and 1 1. So in case of a joint, we are interested in finding the probability that what is the probability of this? What is the probability that both of these will take some value? We are specifying both of them, that the first coin should take value 0 and the second should also be 0, like this. But when we are trying to find the margin probability, we are just interested in that probability that the first coin will take value 0. So we need to add both of these cases. Okay. So it means whenever we are calculating margin probability, we are adding up some joint probabilities. So this is how you calculate a margin probabilities, and it is also a valid PMF. Okay. Then we had conditional PMF for two random variables.
Hello.
So yes.
Yes, so sorry to interrupt. I had confusion in probability distribution and PMF and PDF. How are these related?
Okay. So you said probability distribution.
Yeah, probability distribution, PMF and PDF.
Okay. So probability distribution is a general term which applies to both kinds of random variables, discrete random variables and continuous random variables. In case of the discrete random variable, the probability distribution is represented by a PMF, probability mass function. And in case of a continuous random variable, the probability distribution is represented by probability density function. That's the relationship between them. Those are not different terms but interrelated.
Okay, so probability distribution is how is probability assigned to a random variable?
Yeah, right.
And if it is discrete, it is PMF, and if it is continuous, it is PDF.
If it is discrete, then it is described by a PMF function, another type of function. Okay, and in case of continuous, it is represented by another kind of function. That's the difference. Yeah.
But PMF is also assigning probability to random variable.
Yeah.
Okay.
Value for the random variable taking some value. That's right.
Okay. Thank you.
Yeah. So then we have some discussions about conditional PMF for two random variables. So we have already seen this. What is a conditional probability? What is conditional probability? What is conditional probability? When conditional probability means calculating the probability of some event given that some other event has already happened. We have already seen how to calculate this in the case of a single random variable. But how do you calculate this when two random variables are involved? Okay, so here is an example. The conditional probability mass function of x given y equals y is given as. So this is the notation. So earlier, the probability that we wanted to calculate, this side and this side, both of them were in the x format, right? So for example, let's give you one simple example of conditional probability for a single random variable. So you can say that x is something that represents what you get on a throw of a coin, right? Now, okay, now it's given that what is the probability that x will be 2 given x is even. So this is one example where you are representing the probability that you want to calculate as well as the event on which it is conditioned. Both are in terms of x. So this is an example of a conditional probability in terms of a single random variable. But here we have different random variables on both sides. So x given y. Okay. So x is equal to t1 given y equals t2. So you know the formula. I don't need to explain it. Okay. On the top you will have the joint probability of both of them taking some value together. In the denominator you will have the marginal probability of the event on which it is conditioned. You know this. So you need to know how to calculate the probability, okay? And it will depend on the event. So yeah, you can calculate, if you can calculate the joint probability and the margin probability that we have already discussed how to calculate, you will be able to calculate the conditional probability. Okay. Then we have example of joint distributions. So I have just put two examples. So for example, these are a little bit complicated examples, but try to understand it. So for example, we roll a die. Okay, we roll a die, and whatever the value comes on the die, that many times we throw a we toss a coin. Okay, so whatever value we are getting on rolling the die, we are representing with k. So and suppose the value that comes by rolling a die is 4, then x equals 4, we are throwing the die, we are tossing the coin 4 times. So it means we are how many number of times will we get heads when we are throwing the when we are tossing the coin 4 times? It will be obviously be represented with some binomial random variable with the value of n being equal to k. Okay, so yeah, and this is a related example where how many times we have to toss the coin, that is being determined by the that is being determined by a Poisson random variable. In the earlier case, it was being determined the roll of a die. In this case, it is being determined by a Poisson random variable. So n follows a Poisson random variable, Poisson distribution with lambda, and we are suppose we get the value of the Poisson random variable is some small n, then we throw the die n times. Okay, so in this case also, okay, in this case also, what is the probability of what is the distribution of let's say suppose x represents the number of hits, then what's the probability of this? What is the distribution this is following? Anyone?
If it is rolling or tossing a coin, then it's binomial.
Binomial of parameters. What are the parameters?
N and P.
Yeah, n and p, right. So this is being determined by the Poisson random variable, and this is determined by what is the probability of success or probability of hits. Yeah, so you know x is representing a specific this is a conditional probability, right? But what is the distribution of x? X will follow Poisson distribution, okay, with lambda times p. If it is a pair coin, then it will be Poisson of lambda by 2. Okay, so I told you that I will point out the important things. So this is an important formula that you need to know because questions may come from this. Okay, it's not important. So there is a very long derivation done in the lectures, but you don't need to know the derivation. If you know the result, this is a very important result. Okay, just write it down anywhere and remember when is this being used because this may come in the exam. Okay, so we discussed the joint marginal and conditional PMFs for two random variables. Now we are going to extend that to multiple random variables, more than two random variables. Okay, so the things are not very different than two random variables. If you have understood the case for two random variables, then you will be able to easily extend it to more than two random variables. So what is the joint PMF? In that case, we had the probability that two of them will take some value together. In this case, it is just the probability that all three will take some value together. Okay, and so these are some examples. You can toss a pair coin thrice, represent the random variables x1, x2, x3 with the outcomes of the uh, three coins, and it will represent the case of more than two random variables. Now, how do you calculate a marginal and conditional PMFs? A similar thing is happening here also. So when you are focusing on what happens when you try to find the marginal PMF, you are focusing on a single random variable or a subset of the random variables, not a single random variable, but a subset of the random variables. For example, if you have 3 random variables, then you are focusing on the probability of a subset of them. So in that case, for example, in the 2 random variables case, we had 2 random variables. And while calculating the margin probability, we were focusing on the probability of just a single random variable. And in this case, we may focus on the probability of a single random variable or 2 random variables. Okay, so we are focusing on the a subset. That's what a margin probability represents. And similarly, conditional PMF is represented in a similar way. Okay, so if you have n random variables, then k random variables will be on this side, and n minus k random variables will be on this side. Okay, so for some set of or for some combination of random variable, you will be calculating the probability, and for other combination, you will be conditioning them on. So I hope whatever I am saying making sense, because no one of you responding anything. So any dots till this point?
No.
Okay. Then this is a little bit important. So how do you do the factoring and sequential conditioning? So suppose you have this joint probability, right? You know that if we have to calculate the probability, that joint probability of this x1 and y1, you will calculate it by probability of getting x1 times probability of getting y1 given x1 has happened. Okay, so
Yes.
so in a similar way, you extend it to multiple random variables. Okay, so probability of, so you can start either way. Okay, so I started from here, so you can go other way also. So probability of probability of x1 being equal to t1, then probability of x2 being equal to t2 given x1 has already taken some value. You can write it x1 taken value t1. Then similarly for this case, you can multiply and it will be broken down. That's the way. So it may look like very theoretical, but it will be helpful when you solve some problems. It will be clear. Okay, factoring can be done in any order. So you can take, I have taken here x1, but you can first calculate the probability of y1 times x1 given y1 given x1 has taken some value. Yeah. Okay, so this is a general concept, marginalization, that we have been using for 2 random variables and also more than 2 random variables. So how we do marginalization? By we are ignoring all the other random variables that we don't want to focus upon. So sum over everything you don't want. And what are you summing over? What are you summing?
Probability.
Which probability? Joint, marginal, or conditional? Which probability?
Which is needed only.
No, we are. So what is this? This is joint probability, right? So
Yes, sir.
we are summing the joint probabilities, and summing over everything we don't need. So t1, t2 we will fix in this case, and we will take all of the values of t3. Okay, and whatever the joint probability we will get, that will add up all of them. Okay, so that's why we do the marginalization. So these things are more clear when we have a lot of examples to illustrate, but unfortunately we don't have that much time to
In the
take.
first example, we are wearing T3. In the second, we are wearing T2. In the third, we are wearing T1. Is it right?
Yeah, that's right. So
Okay.
here we are considering, okay, whatever we are ignoring, that's why that's what is here today.
Yes, sir.
Okay, so that was all about week 1. Very simple week. We have some questions. So Naveen tosses a fair coin twice and Suman tosses another fair coin 2 times. Okay, both of them are tossing 2 coins 2 times. Okay, let the random variables x and y denote the number of hits observed by Naveen and Suman respectively. So Naveen and Suman. Okay, Naveen throwing 2 coins. Suppose these are coins. Suman is also throwing 2 coins. So earlier I wrote all the cases, right? 0, 1, 1, 0. I don't need to write it again. So those are the values that it can get, and those are the values that it can also get. Now what we are interested in is, let the number of variables x and y denote the number of hits observed by Naveen and Suman respectively. So what are the values that x can take? The number of hits, that can be 0, 1 or 2. Y will also be 0, 1 or 2. I hope it is clear, right? Very simple.
Yes, sir.
Now whenever you are given this kind of a table and you need to match which one is correct, what thing you will first look upon? That is, you will look the range. Okay, so you
Summation
can,
is equal to 1.
yeah. What did you say once again?
Summation is equal to 1. Summation of all probabilities.
Yeah, that's also a good point. But even before that, just look at the range of values that the random variables are taking. So here you can see that 0 has not been considered. So we can just rule out this possibility, right? Then the second possibility can be, you can add and check whether these are adding up to 1. But if it is taking a time, then you can just check for a few ones. Okay, so you can see that, okay, these 3 are differing in the first possibility. Okay, so it means either this is correct or among these is correct, anyone among these. So then you can successively calculate the probabilities which are different in them, and then find out. You don't need to calculate all of the probabilities, just a few ones. Okay, yeah, so just we had just a single question from here. Now let's come to week 2, because I don't want to put too many questions based on basic topics, because you know how marginalization is done, how to calculate conditional probability. Okay, the main skill lies in, you have been given some word problem and you have to convert it into a probability problem. That is the main skill. Okay, solving the problem is not important. I think that you also know that thing. So once you are given the problem in a correct format, then you can solve it very easily. I know that. But yeah, the skill lies in, yeah. Now what are the things that we are going to discuss in week 2? In week 2 there are several things that is like a continuation of week 1 itself. Okay, so it's like week 1 and week 2 have been divided into 2 parts, but I think that they are not separable. They are just part of the same thing. So here we will discuss when are some random variables independent. So as before in the previous week, first we see when 2 random variables are independent, and then we will see when do we consider that more than 2 random variables are independent. So when are 2 random variables independent? You know that. Yeah, I hope most of you know this.
The
That,
joint are the product of marginals then.
yeah, right. So when you calculate the joint and verify that if all of the if for all of the possibilities you get joint is equal to marginal multiplication of margins, that is independent. Okay, yeah. And this is a very cool thing. Okay, this is a special case. So suppose you had in this question, you would get this kind of a question where you would be asked to check if these random variables are dependent or independent. Okay, what is the first thing you will look for?
Calculate the joint and marginals and check if the
So-
multiplication is same or
So suppose I'm giving you a simple random variable, simple problem, 25, 0.25. Are these dependent or independent? How would you check? This is X.
Dependent, because it has
So you add from left to
zero.
right and you add from up
Yes,
to
sir.
down, and if both the sums are equal, then it's independent.
Yeah, right. So because if you calculate the, yeah, is someone speaking something? No.
Sir,
Yeah.
0 is there, so we can directly say that it is dependent.
Yeah.
Hmm.
And can anyone explain the reason why 0 is causing the problem?
Because
The product of the marginal will not be 0.
Yeah. So in this case,
hmm,
what are the marginal?
0.25.
For 1, it is 0.25, and
Either this side it is 2 point, on this side
Yeah,
it
it
is
is
also
also
0.25.
0.25.
If
yes,
you
The
multiply
total
both of
is
them,
0.25.
this can never be 0, right?
Yes,
So
sir.
this is a special case that is very simple but very, very helpful. Okay. Yeah. So then independence of multiple random variables, same thing happens. So for more than two random variables, we can easily calculate, easily uh, create a table like this. But in case of a three random variable, you will get something like this is x, this is y, this is z. Okay. These are all the possibilities. Okay. So, and here we have probability that x, y, z are taking some value. So in this case, if you see somewhere 0, in this case also, it will be dependent. Okay. So that thing holds here also. And the things are very same here. Okay. Joint, if joint is equal to the product of the margins, then you conclude that it is independent. Very similar. I don't need to explain it more. Okay. Now this thing is very important. Okay. The concept of independent and identically distributed. So whenever you are trying, suppose you are tossing a coin multiple times, suppose 10 times, then what is happening is all of the uh, toss of the coins. Okay, so you are tossing first time, second time, all of those can be considered as a different experiment. Okay, and those experiments are independent. Whatever result you get on the first experiment does not affect what you get on the second one, and so on. Okay. And it has and each of them has the same marginal PMF, so all of them have the same distribution. So those are identical and independent also. In this case, we call them IID. And later weeks, in week 7, you will be studying this a lot. Okay, so this is very interesting when you are dealing with samples. So you may have seen samples and populations. So this will be very helpful. Okay. Now, okay, yeah, I here it's explained in terms of rolling a fair die multiple times, but it holds for tossing a coin also. Okay, then this is also very important part of this week, memory list property of geometry. Can anyone explain the essence of this to me? Okay, so memory list property of geometric says that, just remember this thing, this line, the future does not depend on the past. Okay, so for example, suppose you are playing Ludo, okay, and as you know, if you until you get uh, a 6 on the throw of the die, you will not be allowed to start the game. You take out that discard. So suppose you have not gotten suppose you have not gotten 6 10 times in a row. Okay, so you throw the coin, or for example, yeah, you throw the die, you get some other number. You are throwing it, suppose 50 times. You did not get any 6. Now you may think that because 6 has not come in so many times, okay, the probability of getting a 6 has increased, right? Because this time I will definitely get a 6. Do you think like this ever? Suppose for example, you have to you are throwing a coin 0 0 and you are getting heads. Okay, suppose you are tossing a coin and you're getting heads. Third time you toss, you get heads. So as you go along, is it that you think that the probability of getting a tail is increasing? Do you think like that?
Yeah,
Have
we
you ever-
think.
Yes,
we
sir.
think, right? Because for many times it has not happened. This time it will definitely happen, but it is not so. Okay. At any time, the probability of getting a tails is same or heads is same, right? So if you relate it to the geometric distribution, it is the same. So for example, suppose getting a tail, x is the number of times we have to throw, or the number of times we have to throw the coin, toss the coin to get a tail. So it will not be dependent on any past. So that's what it says. So you can remember with this example, this memoryless property of geometry. It does not remember the memory. Okay. Then in week 2, we have a very important concept, that is function of a random variable. Okay. How do you deal with the functions of a random variable? So for example, you have a random variable. Suppose you throw a die. Let's take the simple example. X, what are the values that it can take? 1, 2, up to 6. Now I ask you, suppose I define a random variable y is equal to x squared. So you know what are the values are going to be, just a squared. Now, how do you calculate the probability? Okay, so it will just map to each one, right? Because the probability of getting a 36 is, hello, what is
Probability
it?
of getting a 6.
1 by
It is
6.
1 by 6. 1 by 6, right? Same as this. But suppose I throw the coin, throw the dice 2 times, and I represent with x and y. The values that we get on both the die, I represent that with x and y. Suppose I ask you, what is the probability that x plus y is equal to 2 or 3? Then there can be multiple values, right? So I have explained this using 2 random variables, but here we are dealing with a single random variable. Okay. So for example, I wanted to explain about many to one functions. Okay. So that's why 1 to 1 means this is a 1 to 1 function. So every element of x, this set of this is mapping to every other element of this. Okay. But suppose we have a random variable which can take values -1, 0, 1, -2, and 2. What are the values that y can take? Are there any other values that it can take? No, right? So,
No. No.
so what are the values that 0 will map to in the set X? Just 0.
2
For
by
1,
5.
it will be
Oh,
here,
sorry,
here.
1
Yeah,
by
suppose
5.
this is
2 by
uniform.
5.
So it will correspond to 2 values, and similarly 2. Okay, so this is an example of many to one function. So we have squared it. Yeah. So this is a case of many to one function. So this is how you deal with functions of a random variable. Now functions of two random variables. Okay, so this is the case that I discussed just earlier, that you are throwing a die 2 times and you are representing the value that you get on both the die as x and y, and then you take some value. Suppose z is the value that you represent x plus y. What is the probability that z will take some value? So you will have to consider all the cases, right? And in week 2, I think you would have got one question where you were given two random variables x and y, and I think there was a problem where the function was defined as max of x comma y. Okay. Suppose this is equal to something 5. These are the values that you get when throwing a die. Then what are the values that z can take? What is the probability? How do you calculate it? What are all the possible pairs for x and y? It will be something like 1, 5, 2, 5, and so on. Then 5, 1, and so on, right? So you will have to consider all the possibilities. Yeah. So found by summing over all pairs where this happens, then when you are trying to find the max, you will do the same thing, and even in the case of minimum. Are these things making sense? If
Yes.
if it is problematic for anyone, you can just unmute and ask, right? Because this is very important, and we will solve a problem based on this. Okay, yeah. So this was all, I think, in the concept of week 2. So now we will solve some problems. So here we are dealing with the function of a random variable. So we have two random variables, x and y, which are IID. Both of them have the same distribution. They are uniform in the range -1, 0, and 1. Now we are defining a new random variable z, which is mod of x plus y. How do you calculate the PMF of z? Can anyone tell me?
Since यहाँ पे since there is a very little cases where very few number of cases to be observed, we can simply just make a table and perform the computation over it.
Yeah, so what are the values? So what is PMF for z? It means you have to know the range of z, what are the values that z can take, and also what are the probabilities with which those values are taken. So you will put all of the possible values of x and y and see what are the values that z takes. Okay. So you see here that what is the range of z? You put x equals 0, y equals 0, you get 0. Okay, you will not get any value below 0 because we have mod here. So you will get 0 when x and y are 0, x is 1, y is -1, and so on. Similarly, you can put different values of x and y and look at what the values you have to put to get 1 here. Similarly for 2. So since you know that x and y are independent, if you need to calculate this probability, how would you calculate it?
Since they are independent, we can always multiply their marginalized forms.
Yeah, so it will be what it will be? It will be 1 by 3 times 1 by 3. It will be 1 by 9.
Yes, exactly.
So you will add up for all of this and you will get 1 by 3 times, sorry, 1 by 9 times 3. So you will get 1 by 3 for taking value 0. And for taking value 1, you have 4 probabilities. So finally you will get 4 by 9. And for 2, you will get 2 by 9 because we have just two possibilities of x and y for which this value can be taken. I think someone is not muted. Abhishek, could you please mute that guy? Yeah, muted.
Sir, can you explain this from once again?
Okay, so this is a case of function of a random variable. Okay, so what is our function? Z equals mod of x plus y. So what you have to do, you have to put all the values of x and y and check what are the values that we can get. So first you will start from 0. Okay, so x can take value 0, y can also take value 0. So z will take value 0. So that's what we have done here. So x will take value 0, y will take value 0, and it will take value 0. Then when x will take value 1, y will take value -1. Both of them will add up to, and then we put a mod. We will get 0. And similarly, okay. So this is the case. And then what we do for calculating the probability that z takes value 0, you will need to add all of these cases. So probability that this happens, probability that this happens, and this happens. So 1 by 3 plus 1 by 3 plus 1 by 3. 3 times, so 1 by 9 times, so it will become 1 by 3. And so on. Is it clear now?
Yes, sir.
Yes, sir.
Okay. So this is the
What
question.
does the absolute value mean then?
Yeah, absolute value means that
The
even
mod.
if the, yeah, it is mod. So yeah, it means you don't have to consider any negative value here. Okay, so this question is also based on the same problem. So we have to find the probability that x takes value 0 given z has taken value 1. So we know this, how to calculate this. Okay. On the top, you will have the joint probability, and on the bottom, you will have z equals 1. So, okay, here I have written x equals 0 and z equals 1. How I have gotten from here to here, can anyone explain? Because x is equal to 0 and z equals 1. How does it imply to these cases?
Because that is the absolute sum of x and y. So we have both the cases, y is equal to 1 and y is equal to -1.
Yeah, right, right. So in both of these cases, z will be 1 because this is just absolute value. So we have to add both of these values, which will be 2 by 9 divided by 4 by 9. That will be 1 by 2. Okay. So these are just questions from the previous terms PYQ. Okay, so you don't need to panic that questions will be very tough. Questions are actually very easy if you are done with the basic concepts. That's why I have tried to focus on the basics. Okay. Now a pair die is thrown 2 times independently. Let x1 represent the number obtained in the first throw and x2 represent the number obtained in the second throw. Define a new random variable z such that, okay, here the function that we are considering is the maximum of both of those random variables. Okay, so we have to find the probability that z will take a value less than equal to 3. What does it mean? Can anyone explain to me the approach?
This means that
Max
please
will
go on.
be
Yeah, please go on.
Can you tell me a few possibilities for x1 and x2? Because
We can take
one
every value from 1 to 6, and then we will consider the case when the maximum would be 1, the 2, and 3, right?
yeah, maximum would be 3. Okay, so it
Max.
means
So it means we will be having the case like 1 3 3 1 2 3 3 2 3 3.
right,
sample space is 36.
right. So it means neither x1 nor x2 can go beyond 3. So it
Yes.
means the so probability that z is less than equal to 3, it means that x1 will be less than equal to 3. So I have here missed one step. So we can write it means x1 less than equal to 3 and x2 less than equal to 3. Okay, and so sorry, and x2 less than equal to 3. Both of them have to be equal to 3. Now, since x1 and x2 both are independent, we can multiply these probabilities. Okay, so less than equal to 3 means 1, 2, 3. So that means 1 by 2. So 1 by 2 times 1 by 2 is equal to 1 by 4. So I think this is very simple. Okay, I hope all of you get it. Okay, then let's start with week 3. So let me tell you, week 3 is very important. Week 3 and week 4 are most important, I would say. Not just from the point of view of quiz 1, but from point of view of the whole course. Okay, so if you have not studied about week 3 and week 4 till now very well, spend some time, okay, learning, because okay, so whoever has unmuted their call, can you? Yeah, thanks. So this is not just important from the point of view of this quiz, but from the whole course. So if you have not studied well, learn this well, okay, because these inequalities will be very, very helpful in the later weeks, and this is very important, I would say. So the very first thing is expected value, and I hope all of you know about this from the school days. So what is expected value? It is just the mean that we knew, but it has a certain formal definition here. Okay, so let me. Okay. So what is the purpose of an expected value? Not just expected value. In this week, we are trying to summarize data. Okay, all of the things that we will study, that is expected value, variance, standard deviation. What these values does is it provides a kind of descriptive statistics. Okay, so it means a single value is describing all the data that we have. Suppose we have 100 students in a class and we have measured the height of all of them, but there is a single data point that can tell us about some property of the 100 students. So we don't need to look at all the 100 cases. So that is about summarizing the data. Okay, so there are multiple examples for this, but how do you calculate the expected value? So in case of when you throw a die, what you do to calculate the mean or average or expected value, you just add up all the values, then divide by 6. So you do this because that is a uniform distribution case. Okay, all of them have the same probability. So it's like 1 by 6 times 1 plus 1 by 6 times 2. So basically you are doing this. Okay, dividing by 6 means you are multiplying. So if you extend from here, it means that if you have a random variable which takes different values with different probabilities, then you need to take this case in a different way. Okay, yeah, Om, you will get the notes. Don't worry, just focus on the session now. So what you need to do? So what is Tx? Tx is the range of all the values that x can take. Okay, so you have to take every t in the range of x, and you multiply it with the corresponding probability with which this value is taken, and you add up all of them. That is how you calculate the expected value. Okay, so these are some special examples that that are just given just for your reference. Now here comes a very important part. I would say it's important. So function of random variables. Okay, how to calculate the expected value of a function of a random variable. Okay, so this is a very cool trick that you will see. So for example, suppose I gave you the example of this, right? Okay. So let me write x is minus 2 minus 1 0 1 2 and y is equal to x square. It can take value 0 1 and 4. Okay, so if you want to calculate if I ask you what is the expected value of y, what you will do? So let's forget this line. I have not done this, so let's delete this. So if I ask you what is expected value of y, what you will do here?
Probability of getting x into x
This is uniform distribution, right?
for all x.
No, I am asking. I have given you information about x, and I have told you that y is a function of x. Now I am asking you what is the expected value of y,
So
not
you
x.
find x square values and then multiply both x and y, and then add it.
Okay. What should I do?
First, you have to find the values of x square.
Okay, x squared. So I do 4 1 0 1
0.
4. Yeah.
And then you have to add up.
Add up. How?
Like
How?
sir, so you have to list the probability, sir. So the probability of getting 4 is 2 by 5, right? You're muted, sir.
Sorry. I was just speaking. So all of you are, what you are doing, you are trying to find the probability that with which this 4 is taken. Okay. Then you will multiply it with the probability and do it like this, right? But what this equation says is that you don't need to know the distribution of y. You just take the function. So I have squared them, that's correct. So 4 times what should I do? So I can just take the probability of getting a -2. What is this? This is suppose uniform. So 1 by 5.
1 by 5.
So then 0 times 1 by 5, 1 times 1 by 5.
Sir, how 1 by 5?
I have considered it x is uniform, right? Uniform in the ranges. So all of the probabilities, this is 1 by 5, this is 1 by 5, and so on. Okay, so probability of getting each of the values of x is just 1 by 5. That's why I have used here 1 by 5. But the critical thing is that you don't need to know the distribution of y. Have I anywhere used the distribution of y here? I have just squared it, right? Is it the clutter that's making you confused? Or is it clear?
No, that is okay. That is clear.
Yes.
Okay, right. So it means we are calculating the function. So we are calculating y equals x squared, then multiplying it with fx. Okay, we are not doing here gx. Gx would mean that we are calculating the distribution of y, but we are doing multiplying with fx. Yeah. So that's what cool about this. Now there are certain properties of expected value. The first one is linearity of expectation. Okay. So if you have two random variables, suppose x and y, okay, and you have to calculate the expected value of x plus y, then you don't need to know the distribution of y first. Okay. So this is again a thing that will make your calculations easy. Okay. So for example, I will give you an example. Suppose x is all the values that are taken when you throw a die, and y is same as that x. If I ask you what is the expected value of x plus y, what will you do? If you go by the traditional method, you will have to how many values will z take? So it will take first of all 2, 3, 4, just like that, right? So how many values it will take?
6 values, 2x.
No, it will take total
It
11
is
values.
10 values, 11 or 10.
So 2, 3, 4, 5.
2 to 12, it's 11, I think.
Yeah, 2 to 12, it's 11. So you will list all of them here, 2, 3, and so on, then up to 12. Then you will write all the probabilities, whatever the probability are there, you will calculate. Then you will do 2 times probability of z getting 2. Oh, no, I'm writing 2 times probability of z getting a value of 2 plus 3 times probability of z getting a value 3, and so on. But you don't need to do this. If you know the expected value of x and y, you can directly do expected value of z is equal to expected value of x plus y. So for calculating the expected value of x, what you need to do? What you need to know? Just the distribution of x, just the distribution of y. Okay. So, and since both of them are identical, both their expected values will also be same. Okay. So it will just be 2 times expected value of x. So this becomes very easy with the help of a property. Okay. So then this is then the next thing is zero mean random variables, where expected value is equal to 0, and it is very important in the later weeks of the course. Okay, so this is not very important here. And this translation, are you compatible with these translations of random variables?
No, sir.
Okay, so whenever you have a random variable x, okay, and you make x plus c, some constant. For example, you had the case of suppose x takes value 0 and 1. The case of coin toss. So you do translate x plus 2. So what will it become? Y will become 2 and 3.
2 and 3.
Right. So when you translate it like this, how will the expected value change? What will be the expected value of y? First of all, what is the expected value of x?
0 and 1.
So suppose
Half.
if this were a fair coin, half half, then expected value or mean would have been just how much?
Half.
Half. Okay. So what will be the expected value of y? It will shift by. It will become expected value of x plus what is the expected value of 2? Expected value of any constant is just
Constant. Yeah.
So it will become expected value of y will become 2 plus half, 5 by 2.
5.
So it gets translated, right? So when you translated x to x plus 2, the value of the expected value increased by that amount, that constant. So if you have a random variable, suppose now instead of doing x plus 2, the expected value of x was half. So if you did x minus half or x minus expected value of x, what will be the mean of this random variable? Expected value of y? It will become 0, right?
Yes, sir.
Yeah. So that's all about this slide. So let's now look at a few examples. So we already know how to calculate, but yeah, discrete random variables.
Sir,
In case of a discrete random
excuse
variable,
me.
we will calculate the
Sir, I
expected
have
value
a
by.
doubt.
Yeah, sure. Ask.
For can we get linearity if there is a different sample space? Is it true for all in all cases?
Different, yeah, does not matter. So here, have we said anything about x and y?
No.
So
X
look,
and
what
Y
is
is
random
random
definition?
variable.
Yeah, holds for any constants a and b and any random variables x and y. Does not matter. Even if,
Okay.
and I have not even written here. Even if they are dependent, does not matter. Even if x and y are dependent, their expected values, the sum of the expected values will be equal. Yeah.
Linearity will hold.
Yeah, even if they are dependent.
Thank you, sir.
Yeah.
So,
Hello. Yeah.
in the equation that x and y in the above where you have made the table, why we have ignored one?
Okay, so since we have z equals x plus y, so what is the minimum value that z can take?
1.
Why? How? Z can take minimum value z.
Oh,
What is the minimum value that x can take? It can take a minimum value 1. Y can take a minimum value 1. So 1 plus 1, 2.
Oh, thank you, sir.
Yeah. Okay, so here we were discussing how to calculate the expected value of a random variable. So in this case, we are calculating for this die roll. So we will add what are the values that this can take. T equals 1 to 6. It will go from t equals 1 to 6. And for each value, we will multiply it with the probability with which this value is taken. So 1 times 1 by 6. You know this, how to calculate it, right? Yeah. And one more thing is that this expected value does not need to be in the sample space. So is this 3.5? Can you imagine when you roll a die? Can you imagine that 3.5 is coming? No, right? it will always take some integer value. So this is outside of the sample space. So this can happen and it is perfectly fine. Okay, so now expected value of function and linearity of expected value. So it is just example. Okay, we have discussed this already. This is one example. So here g of x comma y is a function of x and y, and we are calculating its expected value. Okay, so g of x comma y is x squared plus xy plus this. So we have just broken it down into these parts, and we can calculate it separately, calculate expected value. Okay, so these are just the things that we have already discussed. Okay, now after understanding expected value, we need to understand a spread. And by a spread, I mean the quantities like variance, standard deviation. I think all of you know these things very well, but we will just describe it in terms of random variables very, very fast. So expected value is this kind of a center of a random variable. Okay, but it will not, but for different kinds of random variables, this value can be same. For example, this is a random variable x which only takes value 10, y takes value 9 and 11 uniformly. All of these are uniform. Okay, and z takes value 0 and 20. Now if you calculate the expected value for all of them is 10. Okay, but all of them are different. So how to differentiate between them? So variance and standard deviation is what differentiates between them. Variance is always non-negative. These things you already know, right? I think we don't need to spend any time discussing. So yeah, so here all of this has been calculated. Variance of x, standard deviation. So we see that expected value was not able to differentiate between them, but variance and standard deviations are able to differentiate between them. Okay, so this thing is important here from the point of view of exam. So scaling and translation. So we have seen a scaling and translation of expected value. Here we have it for variance. So if you scale the random variable by a, it's a will come out as a squared. Okay, understand? In the case of a standard deviation, it will come out as mod of that. When you scale the random variable by a, its variance is not affected. While the expected value was being added to it, variance and standard deviation are not affected by it. And I would say that this is the most important thing here in this slide. So this will be used a lot in this week as well as in future also. Okay, so all of you familiar with this equation?
Yes, sir.
Yeah.
Yes.
So
Yes,
remember
sir.
this. Variance of x is equal to expected value of x squared minus expected value of x whole squared. Yeah.
Sir, excuse me, sir.
Yeah.
The session is not live on YouTube. Why?
No, it's not live, but you will get the recording.
Sir, in recording, it will take 2 to 3 or 4 days after recording will be available.
No, it will be available, I think, by this evening only.
I have joined late. That's why I'm asking if on YouTube it will be available. It's quite easy to watch it.
Okay, so I have shared a YouTube link here on the top that is pinned. You can go to that, and here I will share the recording. Okay.
This video.
Yeah, this video. Yeah.
Okay. Thank you, sir. Thank you.
Yeah. So in this slide, we have been discussing example and properties of variance. Okay, so this we already discussed. Now, sum and product of independent random variables. Okay, so we have I said that this right for any random variables x and y, whether they are dependent or independent, the expected value of sum of them will be equal to the expected value of individual expected value. Okay, you add the individual expected value and you get that. But only if x and y are independent, this will hold. If multiplication will only hold, you can take out the differentiation terms separately only if they are independent. This will hold even if they are dependent, but it will hold only when they are independent. And this will also variance of x plus y is equal to variance of x plus variance of y. This will hold only if they are independent. Okay, so remember these things. These are very important. So here I have just listed a few expected value and variance that you can see later. And then this concept is very important. What is a standard random variable? A standardized random variable is something that has a mean of 0, expected value 0, and variance of 1. Okay, so you can do some scaling and you will get to a standardized random variable. Okay, so this is the scaling. I hope all of you know this. This is just to refresh your memory. I have put it here. Okay, so I think here. So now we need to understand association between two random variables. I think this concept you have studied already in stats 1, but you did not study there in terms of random variables, I guess. So here, if we study the association between two random variables as the covariance. Okay, so how do you? So we have worked with. We have not seen how two random variables are related quantitatively. So for example, we have two random variables x and y. So suppose height of a person and weight of a person, that are two random variables. How are they related among each other? If one random variable increases, how does the other random variable change? So this kind of behavior is explained by this covariance property. Okay. So I hope if height of a random variable, if x is the height and y is the weight, what do you think? Which case will hold in this case? Which of these three? Height and weight of a person.
First case.
First case. Why?
I'm assuming that with increase in height there will be an increase in weight.
Yeah, that's right. So suppose we have two random variables x and y. When one increases and the other, when one increases, then that other random variable also increases. In that case, we say that in this case, covariance is greater than 0. Okay, and if this is covariance, this is greater than 0. When one increases and the other one decreases. Can you give one example of this?
Expenses and savings. Expenses increases, savings decreases.
Yeah, right. You're right. So one of them increases, other one decreases. So this is a covariance of 0. And when covariance between the two random variables is 0, it means they are uncorrelated. Okay. So this is the formula for calculating the covariance. Okay, this is a simple formula. You can look at it, but understanding the significance of covariance is important. Now there are two things. Two random variables can be correlated and independent. Do you know what is the difference between being correlated and being independent or dependent? Is there any difference? Correlated means both of them are related, right? And if x increases, then it has no, if x increases or decreases, it has no effect on y. Then we said that x and y are uncorrelated. And we also had another definition where we said that if x and y does not affect each other, then we say that x and y are independent. So are they same or are they different? Anyone? So both of them are different, okay? Yeah, right. Independence is not equal to correlation.
Independence deals with sample space.
Yeah. So, but independence is a stronger measure, okay? It is a stronger. If two random variables are independent, then they will definitely be correlated. Sorry. if two random variables are independent, then they are uncorrelated. Independent means uncorrelated. But if two random variables are uncorrelated, it is not necessary, it does not imply that they are independent. They may be independent. May be independent.
So here the independence basically referring to if we set one value for some if for one random variable, then it will affect the value of another random variable. Whereas if they are independent, I can take any arbitrary value for one and it will not affect the value of other.
Not value. So look, when did we say that two random variables are independent? When the occurrence of one does not affect the other one. Probability of occurrence are not affected.
Exactly. Okay.
But in case of correlation, we also say that when increase or increase or decrease of a random variable, the other random variable does not get affected. In that case, we say that it is uncorrelated. Both of them looks like same, but they are not.
So correlation, we can say that directly proportional or indirectly proportional. Can we relate by this?
Yeah, that's right. So apart from this, there are some more properties of covariance. If you take the covariance of same random variable with itself, you just put in place of y, just put x. So it will become x minus expected value of x whole squared. So it will become variance of x, right? Covariance of x comma y is equal to expected value of x y minus this. So this will be very important when solving problems. And I think we will solve a problem like this. Okay. And it is a symmetric property. Okay. Covariance of x comma y is equal to covariance of y comma x. And this is also important in solving some problems. So are all of you familiar with this? So this will sometimes become useful when solving problems. Okay, so look, what is happening here, I will explain it. So we are trying to find the covariance of a random variable x and another random variable, which is a combination of two other random variables, ay plus bz. We can break it into like this. So we will take a out and we can take x covariance of x comma y and b times covariance of x comma z. So there is one more form of this. So let me give you. If we had covariance of ay, or suppose ax plus by and z, can anyone guess what would be the values?
Exactly. Okay.
A into x plus z.
A
B into y plus z.
A into
covariance of x and z plus b times covariance of y and z.
Yeah, right. So this will follow this pattern, and if you remember this is very easy, but it will simplify your problem very. Yeah.
So can we not do independently? Like
Can we
ay plus bz equals to a small y, and just like in the second step, and we can calculate by covariance of a capital X and a small y as a two variance.
So what you are saying, can you explain once again?
Yeah. Ay plus bz replaced by a small y function, a small y, and then we can calculate the covariance of capital X and a small y, like in
Yes, we can also do
second
that. Yeah.
properties.
Okay. Yeah, but that will make it little lengthy, right? So you are saying that we can replace it with some other random variable y.
Yeah. Yes.
Okay, then you want to calculate for x and y.
Just like in the second properties.
Okay, then how will you? So this then becomes covariance of x comma y. Then how do you convert it into this form? Okay, yeah. So you will, because it is a symmetric property, you can take it like that. That's what you are saying?
Yes, sir. Yes, sir.
Yeah, so what you can do, yeah, it is the same thing. Yeah, so instead of x comma ay plus bz, we could have written ay plus bz comma x, because it is symmetric and it would
No,
have
no,
made
no,
the same
no,
thing.
sir. No, sir. I want to say that AY plus BZ replaced by just like a function, sir. AY
Okay,
plus
okay,
BZ
okay.
is a function of a small y, yeah, other random, just like alpha. And then we can
Hmm.
calculate the independently covariance of X and alpha.
Yeah, you can do that, but but the purpose of this is to make the covariance in terms of x and
Easier.
y only, x, y, and z. But in that case, yeah, that case would also work. But there you would have to calculate the distribution of y, whatever you, or alpha you, whatever you replace it with. Okay. Okay, then we have correlation coefficient. So I think this thing you already know. Correlation coefficient is just covariance of x comma y divided by standard deviation of x times the standard deviation of y. Its value ranges between -1 and 1. Okay, and if its value is 1, it means they are strongly positively correlated. Means if one increases, then other one increase very fast. Similarly, if it is -1, then if one increases, then the second one decreases very fast, just like that. Okay, so a strong correlation, and if its value is equal close to 0, then it means they have 0 or weak correlation or no correlation. Okay, then we have some examples here. Okay, so independence and covariance, yeah, that's what I explained here. Covariance equals 0 does not imply independence, but if x and y are independent, it means they are uncorrelated. Covariance 0 means uncorrelated. Now we have some examples: positive covariance, height versus weight of a person, rainfall versus farmer depth. It is negatively correlated. So suppose if rainfall is very less, then the depth of the farmers will increase very high. Okay, so similarly for IPL, if we have, suppose if there are uh, uh, four wickets gone in some over, it means the player would be able to score very less marks, very less score, right? Because it will take some time to get used to the context, their situation. Yeah, so that's it. Then we have yeah, this is very simple point that I wanted to include here, that um, that will be helpful when we are dealing with inequalities. Okay, so in case of inequalities, we will deal with standard units that we will see now. So there are two kinds of inequalities here: Markov's inequality and Chebyshev's inequality. Okay, so what is this? We are trying to bond probabilities using mean and variance. What is the purpose of this? First of all, let's understand why do we need this inequality. Sometimes what happens, you are not able to calculate the exact probability of some event. Okay? But you will be happy if you are able to get some upper bound on this. Okay, so even if you get some lower bound or upper bound, so suppose you are calculating the probability and you don't get some exact probability, but you are okay with some bound. In that case, you will use inequalities. The very first one and very foundational one is Markov's inequality. Okay, in Markov's inequality, we have to have a non-negative random variable, and we can calculate the probability that it will take value greater than c, it will be less than equal to mu by c. So you can see here, we are not calculating the exact probability. Till now, we have been dealing with exact probability, right? How do we calculate the probability that x will take value 6, like this? But here, we are happy with a lower bound. So this equation, so it will say the result of this will be something like the probability that some random variable will take value greater than something will be bounded by this thing, that it will not be greater than this. Yeah. So we will look at it in the examples, but let's move ahead now. So it is useful only when the mean is known. Okay, this is the proof that you don't need to. Yeah, you can look at it, but not that important. Just the result is more important. So next, based on this Markov's inequality, we have Chebyshev's inequality. So Chebyshev's, the difference, okay, Chebyshev's inequality is based on Markov's, but it can consider both positive random variables as well as negative random variables, and it is more powerful than Markov's inequality, because in Markov's case we only used the information, we only used the mean of the random variable, okay, but we did not use any information about the standard deviation or variance of the random variable, okay. So in this case, but we use the we use the information about the standard deviation, okay. We are also using sigma here, so that's why it is more accurate. It will always be more accurate, okay. So this is the basic form of this, and this is a derived form. So generally you will see there are two forms of this inequality. This is the upper bound one, because it is giving upper bound on the probability, and it is giving lower bound on the probability, okay. So it will also be written like this: probability that x is less than equal to x minus mu, okay. This is greater than equal to lower bounded by 1 minus 1 by k squared, okay. Any one of you confused about this?
Yeah, can you please go through again?
Yeah, so look, purpose of any inequality is to be able to give some lower bound or upper bound on the probability, not to calculate the exact probability, because we are not always able to calculate the exact probability. Sometimes we are happy with just the upper bound, that it will not go beyond this, okay. So upper limit
Okay.
or lower limit, okay. Now suppose we take the example of a coin, for example we take the example of let's take the throw of a die. It can take value 1, 2 up to 6, right?
Okay.
Now if I ask you what is the probability that x will take value greater than 3, you can calculate it immediately, right?
Okay.
You can immediately calculate it, but it in this case you are able to calculate it easily, but in other cases you may not be able to calculate it easily, because in this case it is a uniform distribution and very simple, it has a very simple sample space, so you can calculate it very easily, but in other cases you won't be able to do it. So in those cases you will have to use the Chebyshev's inequality. Let's apply Chebyshev's inequality here. How will you apply it here? So first of all, let's apply the Markov's inequality. So
Okay.
it will be upper bounded by
It will be upper bounded by the mean divided by c, where c is here is 3.
3. Okay, so it means probability that x greater than equal to 3 is something like, is that right?
3, 3, 1, and 5. Okay, yeah, this is right.
Yeah. So it is giving a upper bound that it will not be greater than this. Now let's calculate what is the probability of this exact probability.
Its exact probability will be 4 by 6.
No, it will be 1 by 2, right?
Yes,
3, 4, 5, and
Greater
6.
than 3?
All greater
Oh
than
yeah,
equal
greater
to
than,
3.
sorry, yeah,
Okay.
you are right.
Okay.
It is greater than or equal to 3, right? So it will be 4 by 6.
Yes,
4 by 6.
exactly.
You were right, yeah. So 2 by 3, it means 0.66. So this inequality was saying that it will be less than this value. And it was indeed less than this value. But, it was not very useful in this case. Why?
Yes, exactly.
Because suppose you ask me what will be the stock price of Reliance tomorrow. I say you that it will definitely be less than the actual stock price was 3,000 rupees. Then,
Sorry, your voice was not coming. Again, please.
so suppose you ask me what will be the stock price of Reliance company tomorrow. Okay, I give you that it will
Okay.
definitely be less than 1 lakh rupees. Okay, I have predicted it. Now,
Okay.
actually it is 3,000 tomorrow.
Yes. Yes.
Would you say my prediction was useful?
No, it was not.
Not that much, right? If I had said you, example, 4,000 or something like 3,100, and it was actually 3,050, then somewhat useful. If it
Yes.
is close, then yeah. So it means Markov's inequality is not that great. Okay. But instead, if you use the Chebyshev's inequality, you will get a better bond. You will get this value. You will get that this value has been become very low. Okay,
Okay.
so for that
Got
you
it.
will, but for that you will need to do the calculation. You will need to know the standard deviation also. Okay, and
Mhm.
you will have to express the difference between this in terms of this k times sigma. Only then you can use this. Okay, so actually this is not the actual form of. So do you know how Chebyshev is based on Markov's?
No.
Let me give you a simple example. Okay,
Yes, please.
so
Sir, before that, can you
so
tell me
suppose,
how was it 4 by
yeah.
6?
So probability that x is greater than or equal to 3. It means it can take values 3, 4, 5, 6. There are a total of 4 values, right? Out of 6.
Okay, sir. Okay, sorry.
Yes. So consider this random variable x minus expected value of x whole squared. Okay, so suppose this is a function of a random variable. Okay, so now use Markov's inequality on this probability of. Can you use Markov's inequality on this? How will you use it? X minus expected value of x whole squared is equal to this is greater than equal to some value c. It will be
Mean by C.
mean of this random variable, right?
Yes, mean of this random variable.
Expected value of x minus expected value of x whole square divided by
C.
C. Okay. Now, what is this?
Sigma square. This is expected value of the random variable y.
No, what is this? This is
Oh,
the
okay. Yeah, this is
variance,
sigma.
right?
Okay. Yeah, okay.
So suppose here we could
Sigma
have put
square.
anything, okay? Instead of C, we could have put anything. So instead of C, let's put here K sigma squared. Does not matter what we put here, right? So whatever we put here, we have to put here also. Do you agree?
Yes.
Yeah. So
Okay. Okay.
so instead of C, I have put this thing. I can put anything, okay? But I have just put here in terms of K sigma. So yeah, now what I do, I will take
Yeah, I see that cancels out in the right hand side and 1 becomes 1 by k square.
a square root. I will take the square root on both sides. It will become mod of this. So it will finally become 1 by k squared.
1 by k square.
So that's how you get the Chebyshev's inequality from Markov's. It is very simple. But during this process, accuracy is improved. Okay, if you calculate, so when you are done with the session, just try to calculate the variance of this or standard deviation of this random variable x. Okay, sigma of x, and express this probability in this way. Okay, and calculate this. You will find that this prediction, that that upper bound that is there, it will become less. So it would have been more useful if it gave me value something like 0.7, right, or 0.8. Then it will be more close to what is actual value. Okay. So yeah, so it is more accurate, Chebyshev's inequality. So yeah, this slide is what I was trying to explain in the last thing. So look, we can calculate Chebyshev's and Markov's not just for cases where we are not able to calculate it, but where we can calculate it, but where we are even able to calculate it. So for example, we take the example of binomial. We know that mu is equal to 5, sigma is equal to this value. If we apply Chebyshev's, okay, can you explain? Can you read it in terms of words? What does this probability says?
Probability of x minus 5 mod x minus 5 greater than is equal to 2.
So consider it like a straight line. Okay, so this is your mean. This is your, suppose this is 0, this is 5.
Distance from to mean is greater than
2 sigma. Okay, suppose this is 2 sigma. Okay, so what is this saying is the probability that this random variable will take value in this range. Okay, it is 5 plus 2 sigma, or it is here minus 5 minus 2 sigma. It is okay. It deviates more than 5 plus 2 sigma from its mean. Okay, or more than 2 sigma from its mean. Is it clear? So okay, just break it down. Okay, so x minus 5, just leave the mod here, so it will become x greater than equal to 2 sigma 5 plus 2 sigma, or x less than equal to minus 2 sigma minus 5. Okay, so this is the probability that it is representing. Okay, so yeah, this was all about Chebyshev's. And if you are not able to understand, okay, just to go through this once more and even watch the lectures. It is very critical. Okay, later in week 7 and week 8, this will be very, very needed. Okay, and you have to understand it to go further. But don't worry, this is very simple but very important. Okay, Markov's inequality bonds large values using the mean. Chebyshev inequality refines this by using variance. Okay, yeah. Now let's move to the problem. We don't have very complicated problems, just simple problem. So the probability distribution of a discrete random variable x is given as below. Calculate the expected value of x. You'll be able to calculate it, right? Just multiply all of the values taken and multiply it with the corresponding probabilities. You will get the expected value. Very simple. What about this? Suppose x and y are independent random variables with means are given and variances are also given. We have to find the value of variance of x times y. Here you will just be using the properties of variance. Okay, so it's given that if x and y are independent, then x squared and y squared are also independent. You have to use this and other properties of variance. So we will use the simple that that equality or that equation that you all remember. Variance of xy will be this. You simplify this. Okay. So here you can, this will only hold only when x squared and y squared would be independent, and that is the case. That's why we can separate it out. Similarly, here also expected value of xy, and if you break it up, you will be able to get the answer. Any steps that you are finding problematic here?
No, sir.
No, right? Okay, so here we have just converted into, our goal is to convert it into the mean and variances of x and y, and then you will put the value, get the value. Now let's go to week 4, final week. And I hope all of you are familiar with the concept of continuous random variables from stats 1. It will be a little bit of revision, but little bit of new things will be there. So first of all, what's the motivation of studying about continuous random variables? Because what are discrete random variables? Whenever you have a discrete set, whenever you have a random variable and it can take finite number of values, then in that case it is called a discrete set. But suppose the number of elements in the set is very, very large. In that case, for example, if you are considering material at weight, and we are representing it with some random variable x, then the weights can be anything, right? It will take values even in decimals. So there will be very high number of weights. In this case, we are not, we don't need to, sorry, we won't be able to describe our probability and everything with discretely representing the values, but we will have to use the continuous random variables. That's where the motivation comes from. Okay, so first, if you have seen the lectures or looked at the slides, we had this example where we just plot the histogram. So so suppose we take the intervals of weights. So weights from this to this has this many data points. Okay, just like that. So weight from this to this. Yeah. Now the very first concept in week 4 is a distribution function. So distribution function, you all know what is CDF. Okay? The cumulative distribution function of a random variable is a function. Just like a random variable, just like a PMF, it is also a function. And it represents the probability of x taking values less than or equal to any particular value. It is the CDF at that point. Okay? And I think this property you are familiar with. If you want to calculate for discrete random variable, this holds that if you want to calculate the probability that x will take values between a and b, you have to subtract the CDF at b and subtract the CDF at a. Okay? It has a property that it is a non-decreasing function and takes values in the range 0 to 1. Its maximum value is 1. As x goes to minus infinity, it's 0. These are things you already know, I think, from stats 1. Now, computing probability using CDF. So the most important thing to know in this week is the difference between cumulative distribution functions of a discrete random variable and a continuous random variable. So can anyone, does anyone remember this? What is the difference? Okay, so wait for a minute. I will ask you this question once again, but let's see what there on the slide. So yeah, okay, computing probability using CDF. So this is, we have been given the CDF of a discrete random variable. Okay, we have to calculate the probability. How do you calculate it? It's very simple, right? So if you want to calculate the probability, it will take value between 3 and 10. You will subtract the CDFs at 10 and 3. If you want to calculate the CDF at 17, you will add all the probabilities up to 17 and so on. So this is very simple. Now we have continuous CDF at approximation. So this gets a little bit, it is very conceptual oriented. So you need to understand what's the difference between the CDF of a continuous random variable and CDF of a discrete random variable. So can anyone unmute and explain it? Does anyone remember what I am asking? CDF, cumulative distribution function of a discrete and a continuous random variable. Okay, so no worries if you don't remember it. I hope some of you were just not able to unmute. But look, in case of a discrete random variable, you would have seen that when we plot the CDF function, what happens is there are jumps like this, and whatever the value, suppose here the the value of x was 1, 2, it means suppose this is 1, okay, or this is 1. From here it's 1. So what does it mean? It is a CDF of a discrete random variable. Its property is that it has jumps like this. Okay, it is a stepwise function. And what does the amount of step represent? What does it represent? Can anyone tell me?
This is the probability of that particular number.
Right. Probability that x will take value 1. Okay. And do you see any kind of jump in the continuous CDF?
No, because it is continuous.
Yeah, it is continuous. The how do you define a continuous random variable? Is its CDF is a continuous curve. Okay. So yeah. So how do you approach? How do you get a continuous CDF? When you have a discrete random variable which has a lot of values or lot of intervals, then you can consider that it will it will be like here to here, then here to here. So it will become like a continuous curve. Are you able to get my point? So
Yes, sir.
this is what happens. So when the amount of intervals approaches 0, then it means it will become a continuous curve like this for a continuous random variable. But the property of a CDF function is that it will always increase, never decrease. It will finally become 1, okay? But it will never decrease. Okay, CDFs and random variables. So it is about general random variables. So if you have a valid CDF, what is the property of a valid CDF? What are the three properties of a valid CDF? First, as x x approaches infinity, the value of the probability should be equal to 1. The value of the CDF function should be 1. Okay, and it should be piecewise continuous. These are few properties of a valid CDF. So if some CDF is a valid CDF, then it represents a random variable. Okay, and you already know if it jumps f1 to f2 at some point, then the difference in the CDF is the probability at that point. You already know. And in case of continuous random variable, there is no jump. Okay, there is no jump at any point. So it means the probability of getting any particular value, what is this? It is 0, right?
Yes.
So do all of you remember this? Is it confusing to anyone that the probability of a continuous random variable at any exact point is 0?
Show me.
Okay. So look, forget about any discrete random variable or a continuous random variable. Just think there is CDF. And how do we define the probability? By the amount of jump. Okay. So if there is some jump here, then it represents the probability. But do you see any kind of a jump at any point? X equals 1. No, right? What is a jump? There is no jump. So you can consider like it has no jump, so it has 0 probability. The other way of thinking about this is related to PDF, okay, that we will see later. But in this way, you can look at. Okay. So in case of a continuous random variable, CDF has no jumps or steps. Probability of x taking in a particular value is 0 for all x, and probability of x falling in an interval is non-zero. So if you find some probability at this exact point, it will be 0. But what is the probability of x being between x equals 1 and 2?
It will be this area.
No, it will not be this area. That holds when this is a PDF function. Right?
Yeah, this is CDF, right?
In this case, yeah.
Yeah, so CDF for x equal to 2 minus CDF of x equal to 1.
Right, that's right. So you don't get confused. That happens when you have a PDF, but in case of CDF, this always holds whether it is a discrete or a continuous random variable. Okay, so since we have P at any point, the probability is 0. So this is a very cool thing, that probability that x will be between A and B, whether you include A or not include B, does not have any effect. Okay, so all of you have seen this equation?
Yes, sir.
Great. So remember it will be sometimes you get confused in your own head. Okay, like what is happening? If you remember these kind of little things, then it will become very easy for you to not get confused.
Especially during exams.
Yeah. Sometimes it happens that Okay, in this equation, so suppose you are calculating some Chebyshev's inequality, and you are worried about whether I should include A or not include A. But then you will remember that it is a continuous random variable. I don't need to worry whether I include A or include B or exclude A or exclude B. Does not matter. Okay.
Okay, sir.
So then we have an example problem. Consider a random variable X with CDF. So this is a CDF. Now it's not like black and white, right? A random variable does not need to be a discrete or a continuous. It can be a mixture also. So at some points there is a jump, then it is considered discrete in those regions. Okay, and in other parts it is continuous. Finally it becomes one. So it is a mixture CDF. So it is not continuous CDF or a discrete CDF. Okay, it can happen. So the way in which you calculate the probability in a continuous CDF and a discrete CDF is same. You just subtract the values at both the points. Okay. Since fx is continuous, yeah. So all of this is simple example. Okay. Calculated for this CDF. I hope all of you have done this exercise in your problems. Now there is something called probability density function. How do you get it? So probability, first of all, when we define a continuous random variable, we define it in terms of a CDF, cumulative density function. When we differentiate the CDF, we get a PDF. And PDF is just like a similar thing to PMF. What PMF is to a discrete random variable is PDF to a continuous random variable. So PMF, discrete, and PDF to continuous. So in terms of CDF, in terms of PDF, this is the CDF expressed. So suppose you take the example of a normal distribution, standard normal, for example. Then what is the CDF for this? Suppose you are calculating CDF at this point, minus A. Then it will be this area. So how do you calculate this area? You integrate from minus infinity to this point, minus A. You integrate the PDF function. So this will be the CDF. This is how you get the CDF, right? So CDF is the integral of the PDF. The derivative of the CDF is equal to the PDF. Okay, and suppose this value is 5, a very common dot. Okay, many people get confused here. Suppose this is x equals 2. Does it mean that probability of x is equal to 2? 5, sorry. So you might get confused that how can this PDF be greater than 1? How this height can be? So, this can be 10 also. Do you agree? Hello?
Yes. The probability is that area, right?
Yeah, probability is the area, and this height can be greater than 1 also. So sometimes people get confused. Oh, how it can be that this probability x equals 2 is equal to 10? No, this is wrong. Okay, probability is always 0. So height can be high of this PDF function, but it will be shrinked so that the total area in this curve will be equal to 1. Okay, so that's one important thing to keep in mind. Okay, unlike the CDF, the PDF does not directly give probabilities. You cannot do this. But if the PDF function is high at some point, it means that around this point it takes higher probability. It takes values with higher probabilities than at other points, but it does not mean that it is taking exactly that probability, that value. Okay, so now we have an example of a uniform continuous distribution that is uniform, that is between 0 and 1. This is the simplest of all uniform continuous distributions. Okay, so let's try to draw. So it's between 0 and 1. Its height will also be equal to 1, so that the total area will be equal to 1. Okay, If you want to calculate the CDF at some point, fill between this. The area, this is how you integrate the CDF. Sorry, the PDF. PDF is 1, and you integrate it from 0 to 1, you will get it equal to 1. Okay. So yeah. Now finally we have some most commonly used common continuous distributions. So you may have seen some common distributions in your stats 1 course. Those are, I think, normal and exponential distributions, right? So we have already seen just now continuous uniform distribution. Okay, what is its PDF? It is 1 by b minus a. If it is between a and b, its CDF is this. I think you also practice deriving the CDF from the PDF by integrating from minus infinity to infinity. For exponential distribution, this holds. PDF is this, CDF is this, and this for normal. This is this closely looking, complex looking this thing. Okay. So, but here we don't have any closed form CDF. We don't have a formula for CDF, just like for other cases. Okay. So remember this CDF of exponential distribution comes very handy. It has a lot of uses. Yeah. So that was all. Now let's look at some. Okay. So before going into the problems, do any one of you have any doubts in this section? No, right?
No, sir.
Okay. So this is a very simple problem that I have chosen to solve here. Here we have CDF of a random variable x. It is not given what kind of a random variable it is. We have just been given the CDF. We have to calculate the probability of this. You know how to calculate this, right? So I have done this in a long way, but how will you do it? You will calculate CDF at this point minus CDF at this point, right?
Yes, exactly.
But the CDF at minus 4 will be, what will be CDF at minus 4?
0.
0. So it will just be equal to the CDF at 6. So CDF function is this. So it will be just 1 minus e raised to the minus 24. You don't need to. Yeah, that's what I have done here. Yeah. So that was all that I had to discuss. And this is the end of the slide. If you have any doubts, you can ask now. Or otherwise, we will.
PDF link, sir.
Okay. We will share this through mail. Don't worry. And you know, you will be shared. You will get the link to the recorded session in the mail also, or otherwise I have shared a YouTube link that where you will get the recording also. Both places you can get.
When we will get the mail, sir?
Recording.
By tomorrow. Tomorrow,
No,
12 p.m.
not. I think by today itself it should be processed because it is around a 2 hours meeting, so it does not take more than 1 hour to process. But sometimes Google servers are busy, so it takes time. But most probably you will get it by today or tomorrow morning. Okay.
Or I will also upload in the calendar, so you can check it over there.
Yeah, it will automatically be in the calendar event from where you joined the meeting. Okay, if you don't have any doubts, we can wrap up the session. Thank you all for being here, listening.
Thank you, sir.
Thank you, sir.
Yeah. Bye.
Thank you, Ankit Bhaiya, for the amazing sessions.
Thanks, Abhishek, for this wonderful initiative.
Okay, so guys, those who having maths 2, do join tomorrow at 3 p.m. We have maths 2 session. So, okay, we can stop the recording. Thank you all for joining the sessions.